welcome back everybody to EE290C. So I realize it's been a little while since we last had a quote-unquote real lecture, so I'll sort of remind people where we're at. Before we do that, just from a logistics standpoint, I believe Phase 3 is basically due in 1 week. So hopefully people are well on their way to that. And then Phase 4, there'll be no real surprises there. That's really just going to be sort of putting everything together, making sure all the adaptations work, and getting some behavioral models, and then obviously really finalizing all the details of the stuff you've done, and hopefully actually getting the real circuits built and stuff like that. So obviously be on the lookout for that. But again, there'll be no surprises there. It should be fairly obvious, I think, sort of what's the final phase of the project going to look like. So before we kind of dive back into stuff, which, by the way, as a reminder, we were talking about CDR design, which I'm assuming that now that you guys actually have to do it for Phase 3 will be of particular interest. But before we dive back into that, any questions from the lucky few that are here? You guys start Phase 3, or? Yeah? Okay. Going okay, or?
Yeah.
Making progress?
Slowly.
Okay. All right, well, so if there's no questions on that, then we can actually go ahead and sort of dive back into the material. So again, just as I was saying earlier, in terms of where we're at, we basically started talking about some more of the details of how you actually do sort of CDR, which reminder just clocking data recovery, how you really do CDR designs. So just as a reminder, sort of, let's say, the canonical CDR, and this is, again, all stuff that we drew last time, but this is just kind of a reminder for everybody. The canonical CDR is something where you take the data, and then in some way, shape, or form, you do some sort of phase detection based upon the data and sort of the clocks that you're using to actually sample the data. And usually we do that with sort of a 2x oversampled type of system, where we have actually an edge clock versus a data clock. And then when we see transitions, we detect, are we early or late? We then take those early or late updates, we pass them through some sort of loop filter, and then use that to adjust essentially the phase that we're using to clock our samples with until we get some sort of relatively locked position where basically the number of early and late signals that we get is balanced out over time. Okay? Now, there's many different ways you can imagine to do this. Kind of historically, the first way that people typically would use is the so-called PLL-based CDR. So the basic idea was, kind of very similar to what we just said before. It's just that now for that phase sort of adjustment circuit, we would actually use a voltage-controlled oscillator rather than some other possible method. Now, the issue with doing this was that basically this VCO, especially if you want a pretty wide tuning range, so you can cover lots of different possible data rates, tends to be pretty dirty, meaning it has quite a bit of jitter. And if it has quite a bit of jitter, that sort of tells you that you'd really like to make the bandwidth of this loop here kind of high in order to get rid of that jitter. But then the problem that we started getting into was we said, well, but wait a minute, if we make that bandwidth high, then unfortunately what's going to happen is that all of the jitter that's sitting on our incoming data, which tends to be quite a bit, if nothing else, just due to residual intersymbol interference, then basically if we try and make that loop bandwidth high, even if we're killing sort of the noise from the VCO, unfortunately, it would be passing this jitter from the data itself very heavily or in a very big way into the output, right? So it's kind of this sort of combination of, well, we want to make the loop bandwidth high because of the VCO noise, but we want to make it low because of the jitter on the incoming data. And with this particular architecture, there was kind of no way you could actually do that, right? The two constraints just oppose each other, so you always end up having to choose something that's sort of bad for both of them. Or I should say, moderately bad for both of them. Obviously, at the end, you'd balance the two things out. Okay? So, and this is kind of basically saying the same thing. But basically where we ended up was in talking about, well, okay, it turns out there's one fairly clever but fairly simple thing you can do that really lets you sort of satisfy both of these constraints at the same time. Okay? And the basic idea is the following. So what you essentially say is that, okay, look, let me use some sort of phase lock loop that uses a quote-unquote good reference clock just to generate the right frequency to begin with, or something that's at least close to the right frequency. Okay? So if I do that and I really do have a clean reference, then that means that I can make this loop bandwidth for this PLL sort of whatever it needs to be based upon sort of the noise I have on that reference versus the noise that I would have really had in this VCO. And again, that would tend to be something fairly high if you actually had a clean reference available. Okay? On the other hand, I still, of course, have to recover the clock somehow from my data. So what I do for that is I actually just take essentially the frequency, or rather the clock generated by my PLL, and as we'll see maybe this lecture, if not, then next time, In fact, you often tend to grab multiple phases from that clock, from that ring oscillator. Then what you do is you use those multiple phases to basically generate a controllable delay through what's known as a phase interpolator. So for now, just think of a phase interpolator as just being a way of generating sort of an arbitrary phase clock at the output. Okay? And so then what I do is that with that phase interpolator, then I can still have my sort of bang-bang phase detection, again, just that up-down signal, pass that through some sort of accumulator, and then use that to figure out what are the sort of digital control bits that I feed into this phase interpolator. Where again, that phase interpolator, that's really what I'm going to be using to clock the actual data. Okay? And again, the advantage of this is that this upper loop here can be high bandwidth, whereas this lower loop, which is this is now really the CDR loop itself, that I can make actually very low bandwidth. Because I'm basically taking these relatively clean clocks, and I'm just using them to change the actual sampling phase. Okay? So this was first proposed by a guy named Stefanos Sideropoulos in his PhD thesis. I'll mention him probably a couple more times as we go through the course. He did a lot of the sort of preliminary, I should say, seminal work on sort of these different types of CDR architectures and what the implications and design trade-offs were. So, just keep that in mind. So this was kind of a, let's say, whirlwind, review or a reminder. Any questions on this before we kind of move on, or make sense to people? Oh, yeah.
So if the frequency offset between TX and RX is relatively large, is that true? You still want to keep a CDR loop bandwidth relatively high?
Okay. So the question was, what happens if you have a relatively big frequency offset between the transmitter and the receiver? Do you still actually want to keep the CDR loop bandwidth relatively low? I'm going to talk about exactly that issue in maybe one or two more slides.
Okay.
So it's a great question. And indeed, kind of what you're getting at is that if there's a big frequency offset, even this particular, let's say, maybe not architecture, but this particular implementation that I've drawn may not be the best implementation. Okay, and we'll talk about that more in a whole bunch of detail. Okay? So the first thing that I just wanted to sort of, briefly sort of remind you, which again I think should be hopefully fairly obvious, we kind of talked about last time, I sort of circled or, dotted all this stuff in here. All of that stuff in there is basically digital logic, right? In particular, I usually build this phase interpolator so it has some number of bits of control associated with it. So that always implies, of course, that if there's a finite resolution with which I use to control that phase interpolator, you can never get exactly the right value for the phase, right? All you can kind of do is get close to that value and then jump around sort of in that vicinity, right? So kind of what I'm implying here is that, and as an example, let's just think about a mesosynchronous system, okay? So as a reminder, a mesosynchronous system just means that the frequencies on the transmitter and the receiver are the same, but the phase is sort of unknown. Okay? And the phase could potentially be slowly drifting or changing over time. Okay? So if I use one of these things and it's in a mesosynchronous system, then basically, initially my phase estimate is just going to start, going up and up until finally I get sort of close to where I'm supposed to be. And then if things are, let's say, good, and I'll explain what I mean by that in a second, I'm basically just going to dither right around sort of whatever that phase position is supposed to be, right? So let's say this is kind of somewhere around here is nominally where the phase is supposed to be. Then basically that's sort of, ideally speaking, the point that I would be dithering around, okay? And it may not be exactly 50% like this. If there's some noise or something, then it may actually have, different code densities. But bottom line, it should be sort of dithering around this point here. Okay? Okay, so if that's the case, sort of, from the standpoint of designing this CDR, what do you think are the things that you really care about the most? What are the things that are sort of the most important in this context? What are some important design criteria here? And I guess not John, since I know he knows the answer.
The magnitude of that dithering?
Yeah, there we go. Okay, so the first thing you care about is just the worst case step size, right? Because basically in the, if I have some basically DAC kind of looking thing, right, which is that phase interpolator, which is just translating digital codes into phases, and I know that I'm always going to be sort of jumping back and forth, right? Then what I basically care about is what's the biggest jump that I could possibly be taking. Right? Because that kind of sets the magnitude of the dither that I'm going to be getting in my system. Right? It's absolutely true. Anything else? Or maybe because of this, how do you think you're going to want to tend to design these things? Or what are the other, let's say, considerations here? Yeah?
feed through due to this dithering?
Sorry, say that again?
The feed through due to this dithering? I mean, what the frequency at which it...
Okay, so you said like the frequency at which it's dithering. You don't necessarily have a ton of control over that. I mean, okay, I guess you could sort of change the rate at which you're running the loop and things like that. But basically that dither sort of has to be there, and I think in this particular context, it probably doesn't change the overall performance all that much. You know, okay, maybe there's some second order effects in terms of, you know, the jitter filtering and stuff, but largely speaking, I pretty much have to be sort of jumping up and down pretty much every cycle, because if I'm not, then actually things are even worse. And I'll maybe show that in more detail in a second, but you can imagine if I'm not going sort of up and down every single cycle, that means I'm actually taking multiple steps up and multiple steps down, which means the dither is even bigger. But, yeah.
Time taken to lock?
Ah, okay, so you may indeed care about how long it takes you to lock. That is indeed true. Although, if I'm in a mesosynchronous system, usually I can kind of tolerate a pretty reasonable amount of time. Usually. Because, again, in an asynchronous thing, things are nominally sort of at the same frequency, but just I don't exactly know what the initial phases were. So once I find that, it's just sort of a matter of catching drift types of mechanisms, right? So given that that's actually the case, what do you think you're going to want to do to that step size? So you're really only looking for drift. So what do you want to do for that step size? You want to make it big, small, medium? Yeah, you want to make it small, right? Because basically the size of that step the size of that step, kind of the bigger it is, the faster I can track things, right? The less time it will take me to do that initial lock. And also, you know, if I have some big noise event or some big errors, I'll just very quickly, quote-unquote, correct for them. But of course, at the same time, if I have a really big step, then even when there's no noise whatsoever, I'll just be jumping around with a really big magnitude, right? Okay, so indeed, if I'm in a mesosynchronous system, I'm going to try and tend to make the step size extremely small, okay? And in fact, I may even do things like, you know, run the CDR just for some short period of time, and then turn it off for a while, turn it on again maybe a millisecond later or something like that, just, you know, fix whatever errors were there, turn it back off, and so on and so forth, okay? And obviously the reason for doing that is it saves you some power. It sort of, you know, in terms of, let's say, worst case error, it doesn't really matter, but, you know, it stops you from doing this dithering kind of behavior, at least over long periods of time, right? But indeed, that sort of pushes you to make things very, very small, okay?
Doesn't making the step size small affect the time it takes for you to actually get to the right point?
Yeah, absolutely, right? So indeed, if you make those step sizes very small and you don't do anything else, then initially when you have to sort of cover a very big distance, it's going to take you a long time to cover that distance. But imagine that now once I'm in lock, basically the only thing that sort of tells me how big to make these steps is sort of how big the residual errors I'm trying to track in the first place were, right? And remember we said that, you know, in terms of the CDR, I really don't want to be having anything with very high bandwidth because, you know, kind of no matter what I do, I can't really get things right in terms of the data jitter. So my best bet is to just sort of try and filter it out as much as I can, or to the extent of at least the things that are caused by SI, and then just only track the really slowly varying components that are just statically everything has been shifted, right? Okay, now, by the way, this is not to say that there are not many implications of making the step size small, and we're actually going to get into exactly what some of those issues are in 1 second, okay? Does that make sense? Or?
Yeah, sort of.
Okay, well, we'll keep going, and, you know, if you have more questions, then certainly let me know, okay? Okay, so this was all for sort of a mesosynchronous system, where, again, the trick was, I said, the two clock frequencies are the same, but it's just sort of the phases might be slowly drifting relative to each other, okay? But remember, especially, for example, in your project, in many systems, actually, now you don't have a mesosynchronous, you don't have the same frequency, actually have frequency offsets between the two sides, okay? So what I want to draw now is sort of, and this is going to be just sort of phase versus time. So first of all, I'm just going to draw sort of in blue here. If I told you that I have a frequency offset, what does that translate into from the standpoint of phase versus time? And don't worry about, you know, wrapping and things like that. Just, you know, what's the shape of phase versus time if you have a frequency offset? Yeah, it's just a ramp. right? It's a straight line, okay? So as an example, let's say I have some ramp that looks like this, okay? So let's say that that's sort of my ideal phase that I want to be at, right? Like that's sort of my reference phase, okay? So if we use the loop that I drew earlier, what is my CDR actually going to do? And for now, actually, don't even worry about the size of the steps. We'll come back to that in 1 second. What is the CDR actually going to do?
Going to dither around that.
Ah, okay. So you said that it was going to dither around this. Turns out that's not quite correct. Okay, so for now, let's even assume I'm just going to give you like a magical CDR that has infinite phase resolution. Okay, and I'll just give you a reminder that this is the CDR that we're talking about. Okay, so it's got an infinite number of bits of resolution, but I want to know what happens if you feed a phase ramp into that kind of CDR. So what's going to happen?
You'll end up with a static phase offset.
Yeah, you'll end up with a static phase offset. Okay? So just for those who, we'll actually do a little bit of math to make that more clear in 1 second, but notice there's only one integration in this loop, right? So the only thing that does is if you've only got one integration, and you actually feed something that has basically, let's say 2 degrees of freedom that you have to correct, then guess what? You can't fix both of them. Okay? So again, we'll do that math in more detail in 1 second. But indeed, if you have that kind of CDR, what you'd end up with is something that, in steady state, would essentially have some very well-defined phase error. Okay? And it would indeed be a steady state phase error. Now, having said that, if I really take this region here, and I zoom into it, then of course what the sort of CDR is actually going to be doing is something that sort of it's going to be dithering around, but it's going to be dithering around, but slowly making steps kind of in the right direction. Right? So let's say something like this. Okay? So, and of course I've way zoomed in there. Okay? So there's actually sort of another interesting implication of this. So we said before that we want to make those step sizes really, really small, right? But what's kind of like the zero order constraint that you have to satisfy if you're going to make this thing actually work? And there's some reasonable ppm offset between them.
It can catch up as fast as the ramp.
Yeah, exactly. So here you have to make sure that your step size is big enough to basically, as you said, quote-unquote, catch the ramp. Okay, so for those of you guys who like to think of things of sort of, let's say, a 240 or even 140 kind of context, basically that step size is setting the slew rate of the loop, right? So if I know how fast that loop is updating and what the step sizes are, I know what's the fastest thing I can possibly catch, right? So what we're basically saying is that step size has to be big enough that my slew rate can keep track or keep pace with the slew rate implied by that frequency error. Okay? Does this make sense to people, or?
You can either increase the step size or increase the update time.
That's right. You can either increase the step size or increase the update rate. Now, as we'll sort of mention in one more second, typically, remember, and I guess I'll draw it over here, if I really had something like this, let's say you're building your 10 gigabit per second link or 12 gigabits per second or whatever, that's a pretty hefty update rate, right? Now, to be totally fair, you're not always going to get updates, because not every single data that you get has a transition embedded into it. But still, that's actually a pretty high data rate to be doing any kind of computation on, right? And remember, especially if we're just looking for things that have pretty low bandwidth, it's kind of a waste to be doing 12 gigahertz logic on something that's only drifting at, degrees per millisecond, right? So, in fact, typically what you'll do is you'll not really work on this full rate data, but you'll actually decimate it. You'll actually send it to some lower rate and then work on things at that lower rate kind of thing. But again, we'll talk about that in more detail in 1 second. So before we do that, I did want to mention one thing, which is, as I sort of pointed out earlier, there is indeed going to be this static phase error here, okay? And again, the reason for that is basically fairly simple, okay? So let's just think of this as basically being, again, I know that this is actually, a bang-bang loop with, finite resolution and all that. But from the standpoint of this particular behavior, it doesn't matter too much. So let's just pretend that the CDR is basically a first order system. Okay? So if you guys remember, in sort of any linear system, if you want to know what the final value of that linear system will be, then you can just use the final value theorem, which just says that whatever your sort of transfer function is, you just take the limit as s goes to 0 of s times that transfer function, and that will tell you what the final value of that thing actually is. Okay? So let's just see what that would imply in this particular case. So first of all, if I have essentially a frequency error, we said that that translates into a phase ramp, right? Okay, so in the S domain, what would a phase ramp be represented as? Assuming that, let's say I'm working on everything now as phi of S. So what would be the sort of representation of a phase ramp?
S time.
And remember, it's a ramp. So what's a step?
1 by s squared.
Okay, there we go. It's 1 over s squared, right? A step would be 1 over s. A ramp is 1 over s squared. Okay, now, just to sort of get, let's say, the dimensions right, it's going to be some frequency offset divided by s squared, right? Because that frequency offset tells you sort of how quickly the phase accumulates, right? But that is indeed going to be your phase ramp. Okay? Okay, so now if that's the phase ramp, then as we said before, the CDR, let's just pretend that it's basically a first order loop, right? So in other words, my model for the CDR is going to look something like this is my phi ref. There's going to be some sort of, integration here, and let's actually maybe even add in some gain. Then that basically just feeds back directly to the input. Okay? And of course, we can call that, let's say, phi out. Okay? So of course, my phi out over phi ref is just going to be something like a over s divided by 1 plus a over s. Right? Which again, if I just sort of simplify things out into sort of a more, let's say, standard form, that would just end up being 1 over s over a plus 1. Okay? Does this make sense to people, or? Okay, so by the way, the units of that gain there are now just obviously in time. You can interpret that, or excuse me, actually as yeah, that's right, as in time. No, actually, excuse me, it's actually in frequency. Right, just to get the normalizations right. Okay, so at the end of the day, remember what we're interested in is how big of a phase error do we have? So in other words, if we're interested in the phase error, we're interested in phi out minus phi ref. Right? Okay, so just to sort of make things a little bit easier, I'm going to assume that my phi out is actually something like 1 over 1 plus s over omega bandwidth. Okay? Just because, if it's a first order loop, all I really have to say about it is that what is the bandwidth of that loop? Because I know that the gain at DC is infinite. There should be no DC error. So really, that's all I have left to talk about, right? Okay, so now if I want to know what's the steady state phase error, then again, really all I have to do is I take the limit as s goes to 0 of s times that input reference, which is delta omega divided by s squared. And then my error, since I'm interested in phi out minus phi ref, I can just say that that's phi ref times 1 minus, or I'll do it the other way. I'll do it as phi out minus phi ref over phi ref minus 1. Right? Okay? So if I do that, then I'm just going to get, if I obviously write all these things out, 1 over s over omega bandwidth plus 1 minus 1. Okay? Everyone tracking so far? Or? Okay, so now actually it's just a matter of doing a little bit of simple math. Right, so when you subtract this 1 over here, then basically at the top you're going to end up with something that looks like s over omega bandwidth divided by s over omega bandwidth plus 1. Okay? Maybe there's a minus sign there, but it turns out that doesn't really matter. We'll put that in. Then, of course, this s will cancel with that squared, so I end up with delta omega over s. Okay, so then that S cancels that S. I take S equals 0, the bottom just goes away, and what you end up with is delta omega over omega bandwidth. Okay? So in other words, what this tells you is if you put that ramp into the first order system, that first order CDR, then what's going to happen is you're going to end up with a static phase error that's basically proportional to the rate of that ramp relative to the bandwidth of your loop. Okay? So now, why is this, again, kind of bad news from the standpoint of everything that we've been talking about up until this point?
We want to lower the bandwidth to save energy.
Okay, well, we wanted to lower the bandwidth for a couple of reasons. Potentially lowering the bandwidth gives you lower power, but in fact, not only that, we said that lowering the bandwidth gives you smaller steps over here, right? It gives you less dither. We said that it allows you to filter out the junk that we know that's going to be on the edges more, right? But now again, we have this opposing constraint, which is that even though you'd like to make the bandwidth low, what you actually have to do is make it reasonably high, or at least higher than you may have liked, just because if you don't, you're going to end up with this static phase error. Okay? So, by the way, Joshua, I think this is, addressing the question you were asking earlier.
Yeah.
Okay? So, now the question is, just one thing that, is going to make life actually a little bit worse, which is that, as I was mentioning before, right, those updates are coming at a pretty high rate, right? So if I'm running this thing at, let's say, 12 gigahertz or 12 gigabits or whatever it is, I'm going to be getting these updates at a 12 gigahertz rate, or 12 gigasample per second rate. And that's probably much, much faster than I really want, right? That's probably much more sort of data than I can really effectively use, or at least building the digital processing to run at that speed will probably cost me quite a bit of power, okay? So to make life sort of even a little bit worse in terms of these trade-offs, in terms of sort of what the loop bandwidth would be versus, how fast of a ramp can you track, turns out that typically speaking, you won't really run this thing at the full rate, but instead what you'll actually do is deserialize the data first. And what I mean by deserialization is just basically that, if let's say that this was my data sampler, and this is my edge sampler here, so that's my data clock, this is my edge clock, then what I will basically do is shove this into something that sort of looks like a big bank of flip-flops, okay? Where there's basically going to be sort of two clocks in here. One is sort of equivalently the data clock, meaning as an example, 12 gigahertz if you're doing a 12 gigabit per second link. And then the other one would be something like the data clock, just as an example, divided by 10. Or maybe divided by 12, or even maybe divided by 24, or something like that. Okay? So the idea would be that, if I have my incoming data stream that's coming in at, again, let's say that 12 gigahertz or 12 gigabits per second. So this is my so-called serial stream. And the parallel stream would basically be, if this is, let's say, A, B, C, D, the parallel stream would be something like, I have this A for some period of time. I also have that B for some period of time. I have that C on some period of time, D, and so on and so forth, right? So what I'm basically doing is I'm just taking this high-speed serial data, and instead of having sort of, let's say, 12 gigabits per second on one wire, I could have 1 gigabit per second on 12 wires each, okay? So obviously the net throughput is the same. It's just that now I'm sort of translating it to a lower individual sample rate, but with more parallel wires, okay? So typically then what will happen is you'll take all of those parallel things, and what you'll usually do is rather than just sort of, do all the same computations you would have before, you'll just look for some aggregate behavior. So you might say, okay, well I had, 12, let's say I do a divide by 10. I may have had 10 possible up and down signals, right? So what I may do is I say, okay, well, only if I get, let's say, more ups than I do down across that whole window, only then will I actually move up, right? Or maybe only if I got, 2 more ups than I got downs, only then will I move up, right? And so on and so forth. So that's usually what's known as sort of majority voting or some transition filtering or something like that. Again, very common thing to do in these kinds of designs, if nothing else, just to reduce the amount of sort of computations that you end up doing at the end of the day. Okay? And again, this is kind of important in this context because it puts in some practical implications about really how fast you want to be running these loops. Okay, and sort of really how you end up wanting to design these things. Does this make sense to people, or? Okay, so just to sort of come back to here, we said that, if we really did have this plesiochronous system, with that CDR that I drew before, then we again had this bad situation where we have this trade-off between sort of how fast can we track those ramps, and therefore how much static phase error are we going to get, versus sort of how much can we filter out the ISI jitter. Okay? So what do you guys think we're going to do? How are we going to fix this problem?
We have the same problem in PLL, so put one more.
Yeah, there we go. Exactly. So what you basically said is, well, look, what you've basically said is that now, rather than me being able to just looking for phase, what I should actually do is not build a delay lock loop, but actually build a phase lock loop. Okay? But just to make sure that this is sort of clear, we're going to sketch this out because, remember that phase lock loop is still sort of, separate from the real phase lock loop we're using to generate the clock in the first place. Okay? So let's just draw sort of what this looks like. Okay, so again, we're going to have some reference clock. We're going to have some main so-called clock generation PLL that we're going to use to generate that reference clock. So again, our sort of standard PFD, loop filter, VCO, of course, feed that back. So then divide by some n, feed that back to there. Then again, I'm going to take the multiple phases out of that VCO. I'm going to feed that into some phase interpolator. And of course, just like before, I'm still going to have some bang-bang phase detector. So this is my data. And of course, feeding into here is sort of my either data or edge clock. Okay? But now what I'm going to do is, as we said, instead of making sort of this loop filter here, only have one integration in it, now actually I'm going to have two integrations. Okay, so let's draw sort of what that would look like. So for reasons that will hopefully become apparent in 1 second, let's just say I put some gain, then I accumulate the thing once, I accumulate the thing again, and then I feed it to my phase interpolator. Okay, so now, if I'm really building the equivalent of a PLL, or actually just in general, will what I just drew here work, or will this have a problem? Yeah, it's unstable, right? I just put two integrations in the loop with no stabilization, no zero, no nothing, right? So how do I add the zero in? Yeah, I have a feed-forward path, and in particular, when you say feed-forward path, like where does that get added in?
From the output of the first accumulator.
Yeah, exactly. So if I want to do sort of just by direct analogy with a normal PLL, I'll have something that's usually called the proportional gain, and I'll have that jump around sort of the integral section, and then feed that proportional gain into the last accumulator. Okay? So now indeed that bottom thing that we drew there, even though this is the CDR, and even though, by the way, almost all of this stuff is actually digital, right, what we're basically doing is building the equivalent of a phase lock loop. It's just that we know that the sort of frequency range that this phase lock loop needs to handle is probably way, way smaller than the frequency range we had to handle here, right? Because here we're really just looking for sort of a ppm offset between the reference crystal on our chip and the reference crystal on the other thing that we're talking to, okay? So again, just to sort of make sure the intuition is clear, this register here would sort of be the frequency register, and that output over there would sort of be the phase register. Right? So the frequency register sort of tells you, okay, what is that ppm between the two clocks? And the phase is telling you, okay, well, what's actually the instantaneous phase value that you should be using to then, of course, control this phase interpolator here. Okay? Does this make sense to people, or? Okay, so these sort of second-order, CDRs are now actually very, very common. Because what's nice about this is that, notice, now you can really sort of decouple the loop bandwidth from essentially any steady-state phase errors due to that frequency offset, right? Because now, as long as you've sort of built the second-order loop right, essentially that extra integration will make it so that rather than you getting sort of a trajectory that looks like that, now if you've really done things right, and I'll just draw this in black, now what should really happen is that it actually locks onto the right position and then tracks it. Right now, of course, there's still going to be the dither around there, But at least now the size of that dither is not set by sort of directly, at least, sort of the frequency error that you're tracking. Okay? You still have to make sure that you can keep up with that ramp. But the good news is that since we're only going after a few ppm, that's usually a pretty easy thing to do. Okay? Okay, so really the kind of, let's say, the higher order bit to keep in mind here is that whenever you're building these sort of CDR types of loops, the really important thing for you to look at is just what is the phase offset trajectory. Okay, and by trajectory I really mean, we said that in a mesosynchronous system, the phase versus time is basically constant, right? So it looks like that. And that means that when you build the loop, a first order loop is sort of fine, because you just have to sort of figure out what that offset is. If I have a plesiochronous system, then now my trajectory, has this ramp. So again, I better build my loop so that it can estimate both, sort of that offset and the ramp rate, right? And in fact, turns out you can even do more sophisticated things like, for example, sometimes people have phase offset or phase trajectories that even look something like this. Okay? Anybody know where that actually happens to come from?
The offset is also varying.
It is indeed varying. It turns out in this particular case, it's actually being varied intentionally. So maybe
Supply.
Say that again?
Supply?
Supply. Well, no, okay, I mean, you could vary the supply to create this to happen, but it turns out that, people want things to look like this. Like, again, they'll actually work really hard to make their PLL on the transmitter side intentionally do this. So, any thoughts as to why you might want to do this?
Oh, is this like a spread spectrum clocking?
There we go. It's a spread spectrum. Okay, so sometimes you're worried about, some spur coming out of your chip. And if it has too much power spectral density, then, the FCC gets unhappy or something like that. So sometimes what you'll do is indeed this spread spectrum type of technique, where you intentionally spread the energy of that clock out over a band of frequencies. Okay? Well, if you're going to do that, then that means that indeed your phase is going to have this weird looking behavior on it. Right? And it may even actually, continue and just have these weird like circles and things like that. Okay? So kind of again, the key point is that if you know that you're going to have some weird trajectory in the phase, you should build your CDR loop so that it can figure out what that, all the deterministic components of that trajectory actually are. So if you have like a spread spectrum design, you'd want something that, would not only figure out, what the frequency offset is and what the nominal phase offset is, but in fact what the spreading frequency is, what the spreading rate, and so on and so forth. Okay? That's probably more, there's not too many systems that you will deal with that have to deal with that. But, it's again something important to know about because it does get to this sort of general principle of designing your CDR loop so that it indeed tracks with whatever the sort of trajectory of your input is doing. Okay? Any questions on this before we move on? Or
How do you do that actually?
Say that again?
How do you do that spreading?
Okay, there's lots of different ways you can do it. Among the choices of techniques are things like adjusting this divide ratio dynamically, and in fact usually use some fractional NPLL for that. In fact, there's some similar examples that we'll walk through in a second where, let's say you had some phase interpolator at your output, and then instead of tying it into a feedback loop, you had some deterministic trajectory you created through that phase interpolator. But basically pretty much anything that mucks around with the PLL, you can use to create really weird looking trajectories, especially if you know what it is that you want to do. Okay? Not to say that it's an easy thing to do, but there's lots of, let's say, different ways that can potentially be done. Okay? Now, there is, let's say, there's a couple of interesting practical issues. Okay? So far I keep drawing this loop as if there's really just sort of one output from that phase interpolator. To be totally fair, even sort of our standard thing, there's probably actually two outputs, right? Because usually the way we do that bang-bang CDR, at least if I have a full rate system, is I basically have clock, and then I use clock bar for my edge samples, right? But okay, maybe that's not so bad because you could imagine you could just take your phase interpolator and then do some sort of phase splitting kind of thing and get both clock and clock bar with kind of the same, let's say, phase relative to the reference clock. Okay, so that seems sort of reasonable. So let's call this is, let's say if we have the full rate design. Okay, but let's say that we actually wanted to use multiple clock phases. So we actually wanted to do time interleaving because let's say we want to run really, really fast. Much faster than sort of nominally we could get an oscillator to run, or maybe not at least a ring oscillator to run. Okay? And let's even just take the simple example. Let's just say that you do what's called double data rate, which is often referred to as DDR. Okay, so here I'm basically going to be getting, if I look at my clock, then what I'm basically saying is that I'm going to be capturing data both on the rising edge of the clock and on the falling edge of the clock. Okay, so this would be my data clock. Now remember, you still also have to do timing recovery, right? So if I also have to do timing recovery, that means I now need another clock that basically is 90-degree phase shifted with respect to the first clock. Okay? Okay, so now the question is, how am I going to build this? How am I going to support this in my CDR hardware? And first of all, what are just some of the options that I might have? And remember that, this data clock is not really a fixed phase position. It's actually moving around based upon my CDR updates. And you want that edge clock to also move around kind of the same way. So how might you build this?
And you just interpolate from the phase interpolator again?
Interpolate from the phase interpolator. What exactly do you mean?
What I mean is, can you use the same 4 phase inputs and generate the edge clock also?
Okay, yeah, absolutely. So you could indeed, right? I've got 4 phase inputs into that phase interpolator, giving me 1 output. Well, I could indeed just copy the phase interpolator, take those same 4 phase inputs, but just sort of rotate the code by 90 degrees, right? So if let's say this is, some phi, I can make this phi plus 90, right? And then indeed, I'll get 2 output clocks, which at least nominally would be separated by 90 degrees. Okay, so this works. By the way, there's some people that do what's called QDR, which means the clock is 4 times slower than data. We could even do, and I don't even actually know how to call this, but I guess that would be ODR or octal data rate or something like that. So you can even do 8x interleaving, 10x interleaving. You can even go bonkers and do 100x interleaving if you really wanted to. But so what's kind of bad? What would start happening if you actually had to support that kind of system? Let's say even with a QDR kind of system, so quad data rate. How many phase interpolators would you need to support that? Yeah, you'd want 4 phase interpolators, right? If you have 8, you'd need 8 phase interpolators and so on and so forth. So first of all, what's the obvious thing that's kind of bad about that?
Power and area.
Yeah, power and area. Okay, and then the second one is
Mismatch.
Yeah, mismatch, right? So the obvious one is that just first of all, even if they were all the same phase interpolators I had before, they're gonna just burn more power, right? Just linearly with the number of phase interpolators. Now that's not exactly true because the frequencies maybe aren't fixed, but roughly speaking, power and area goes up, right? The other issue is what Chintan was saying, which is, look, now I have 2 physically independent structures, and I'm kind of relying on those 2 being the same as each other, right? Because if they're not, then that means that I'm basically going to get errors in this 90-degree spacing here. And those errors are going to translate into potentially me not being locked to the right clock position relative to my data, right? So that's not to say that it sort of can't be done, but it turns out there's a sufficient amount of annoyances with doing things this way that people actually came up with a few fairly clever solutions that basically allow you to equivalently build just 1 phase interpolator, but actually get multiple clock phases, all with that sort of phase interpolation happening on them, all at the same time. Okay? So, to see how you might be able to do something like that, and we'll go through sort of a couple of these examples. The first one actually is fairly clever. So what they basically do is they say, well, okay, look, if I've got, some VCO that's sitting inside of a PLL, well, if I can just somehow nominally move the phase of that VCO around, then basically, automatically, if I really have a multi-stage ring oscillator, so you should keep in mind that what's inside of here is just something that conceptually looks like a bunch of inverters tied back to back. Okay, and I guess I'll draw it so there really are 4 phases here. Right, so something that looks, say, like this. Okay? So if I can just make it so that I just shift basically whichever phase it is that I use to take the feedback off of. Right, so let's say that's my PFD. That's my reference clock. And I'll just draw my loop filter here. Actually, I'll really draw it this time. So now I'll actually draw the charge pump just because you'll see in 1 second I'm going to be mucking around with that a little bit. Okay, so that's my charge pump. Of course, my loop filter. Okay. So the basic idea is if I can just, hack it so that somehow this phase over here changes, and changes in some controlled way, then actually I can make it so that all of these phases move together, right? Because the feedback is going to force one of these phases to track with whatever sort of offset I introduced. But then all of the rest of them, because I know it's a ring oscillator, are all just directly related to the position at which I put that one nominal phase in the first place, right? So conceptually, does that make sense to people in terms of, the trick I'm trying to play? I'll take that as a yes. Okay, well, so just to see if it really makes sense. So what's one of the ways you could use to introduce a phase offset into the PLL? And I'll give you guys a hint or a reminder. There was one particular thing that we talked about in some reasonable amount of depth that caused a problem with static phase offset. Anyone remember what that was? I heard somebody whisper it.
Just have some mismatch on the charge pump current.
Yeah, right? Remember we said that if we have mismatch in the charge pump currents, that, for example, let's say, your I up nominally looked like that, but let's say your I down, let's say if it was for the same nominal width, was, let's say, larger, then we said that the loop would actually compensate for that and make it so that the net charge in both of those was the same, right? And the only way to do that is, of course, to make the up wider than the down. And if the up is wider than the down, that implies there's a phase offset. Okay? So it turns out the way you can actually do this is quite clever. What you basically do is, if you want to intentionally introduce an offset, you just intentionally skew the up and down currents. Okay? So in this particular example, what you might do is, whatever CDR sort of control bits you had, you would use those to actually program the down current relative to the up current. Okay? So by the way, I should mention this was, I believe, first sort of proposed by, in a paper that was written by a guy named, I can't say his first name, so I won't even try, Jackie Wong. So that's where the J comes from there. And this was in JSSC in April 2004. Okay? So basically, it's still allowing you to do sort of a dual loop CDR, because the bandwidth of the CDR itself is still going to be set by basically the accumulators and everything that you put before this. Right? It's just that you're going to be sort of hacking the characteristics of the PLL in order to get that phase offset on multiple phases all at the same time. Is this clear to people, or? Yeah.
When you have this, if you look at CDR, you also introduce another integration? Or?
Okay, so it's a good question. So the question was, well, if I really do this, then it looks like my CDR updates are actually going through the PLL loop, right? And so the question was, are you introducing an additional integration onto the CDR?
Or it's the bandwidth is too high than...
Yeah, okay, so the real trick is that basically you can't really tell the difference between hacking on this and sort of just, changing the phase of the reference. So effectively the transfer function you're going through is the same transfer function experienced by the reference. So to the extent that this loop bandwidth is pretty high in comparison to your CDR loop, it doesn't make a big difference. Now you're absolutely right that if I wanted a very high CDR loop bandwidth, then this would be a problem, right? Because it introduced additional filtering and phase shift and etc. into my CDR loop. Does this make sense to people, or? Okay, so it turns out there's actually a few other ways that you can play sort of the same trick that may have some slight preferences in terms of the implementation details. So to sort of, let's say, motivate why you might want to do something else besides this, because this is actually a pretty clever way of doing things. Remember that we talked last time about, you may actually want to be able to do 360 degrees of phase shift, right? Because it may be that, in particular, for example, if you're doing one of these plesiochronous loops, right, that actually this register here is going to wrap over, right? At some point, to create that frequency thing, you actually have to wrap the full 360 degrees of phase, okay? So what's kind of painful about doing that in this particular design? Why does that kind of suck if you want to have the thing wrap?
It's analog. It's analog.
Say it again?
It's analog.
It is analog, but like let's be more specific. Like what would you have to do when the thing wrapped?
Take your current from high to low? Or...
Yeah, exactly. What you'd have to do is you have to figure out what's the magic current level that at the high level, if I flipped it back to the low level, give you this exact 360 degrees of phase shift, right? It's not to say you can't do it, but it's definitely a lot more painful than, for example, with these phase interpolator kind of things, or in the phase interpolator, and we'll talk about that in more detail when we show sort of exactly how that's built. But conceptually, in the phase interpolator, since you're just picking different phases, it's a lot easier to do that wrapping, right? Because you just pick a new phase that basically corresponds again to 0 degrees, okay? So because of that, there were indeed a couple of, let's say, follow-ups from this that were essentially trying to still allow you to do that 360-degree phase wrapping kind of behavior, but still allow you to generate multiple clock phases all at the same time, okay? So there's actually sort of two versions of this that are in many ways sort of very equivalent, but let's say have some slight, differences between them. So the first one is still, very similar idea. We're still going to be essentially hacking things in the PLL. But this time, instead of mucking around with the charge pump itself, what we're basically going to do is we're going to take those multiple phases from the VCO, and this time I'm actually just going to put a phase interpolator. Instead of using that to directly generate the output, instead I'm going to take that phase interpolator and use it to provide the feedback for my PLL. Okay? Where now again, this phase interpolator here is of course controlled by the CDR control bits. Okay? So the idea here is actually very similar, right? Because now what you're doing is that instead of introducing that phase offset in the forward path of the loop, instead what you're going to do is just introduce the phase offset in the feedback path of the loop. And again, the advantage of doing that is that, by doing this offset in the feedback, I just have to offset one of the phases that I'm using to feedback, and all of the rest of them will naturally track. Okay? Now, it also has the, let's say, the limitation or the, let's say, the caveat that now these updates, the CDR updates, experience the PLL feedback transfer function. But again, since you typically want a low CDR bandwidth anyways, that's not too big of a deal. Okay? So this particular idea, I believe, was sort of first published by some people from IBM in Zurich. So that's Thomas Toffel, and I believe this was in ISSEC 2005. Okay, so fairly shortly after sort of the previous work that I mentioned. Okay, so this, again, indeed actually works pretty nicely. Although notice it does actually, it's not too horrible, but it does introduce some extra sort of high-speed hardware in the sense that, you have this phase interpolator that's, still working at that, whatever the clock frequency actually is. Turns out there's one more trick you can play that gives you sort of the same effect of doing this phase interpolation, but actually doesn't really require any high-speed hardware. At least conceptually doesn't require you to have the high-speed hardware. Okay, or at least, maybe it's just another way of building the same thing. Okay, so, I don't know, anybody take a guess? What else could you possibly do to essentially introduce a phase offset into the PLL, basically by blending between multiple phases, but not necessarily doing it at the full speed of those clocks? Any thoughts? And by the way, this is kind of a subtle thing, so we'll see if anybody can just throw some wild guesses out there, and we'll see if we can get it.
Can you keep muxing between certain phases? Or?
Okay, you could do that. You could basically on one phase pick one thing, and on the on one clock cycle pick one phase, and on the next pick a different phase. You could indeed do that. And that actually does work. Although that has the unfortunate characteristic of, because you're generating these big jumps, you then have to sort of make the PLL sufficiently low bandwidth that it filters those jumps out, right? So you could do that, but unfortunately that has some, let's say, not so good implications in terms of the PLL loop bandwidth.
Can you
Yeah, go ahead.
alter the transfer function of the phase frequency detector?
Ah, okay. Now tell me a little bit more about that. So what exactly are you going to do?
Well, first, since you said you want it to be at a lower rate, your updates are coming at free-ref. So, I mean, ideally, the phase should be locked to like quadrature or something. Or depending on the lock point, you can probably change insert some offset into the comparison between the two phases.
Okay, you could do that. Remember, I want a full 360 degrees of range, and I want to do that sort of in a fairly transparent way, but you're absolutely right. I could just somehow muck with the phase frequency detector to adjust its offset. There's something else we can do that mucks with the phase frequency detector that's, again, kind of subtle, but go ahead.
Can you put like 4 divide by n's and then do a PI?
Yeah, there we go. Okay, so that's indeed pretty much exactly what you would do. Okay? So imagine that, and this is obviously going to get a little bit more painful to draw, so forgive the clutter, but we'll try and do this as cleanly as we can. Let's say that just conceptually, instead of just having one phase frequency detector, conceptually imagine we now had 4 of them. Okay? So the reference for all of them will always be the reference, right? That I'm not going to change. But now what I can do is, if I actually have 4 phases feeding back from the VCO, I could feed each one of those phases independently into each one of those phase detectors, right? So let's say I had a 0-degree clock, a 90-degree clock, a 180-degree clock, and a 270-degree clock. Okay? Well, so now if I do that, and now you should sort of think of these things as, the output of the PFD maybe sort of includes, well, okay, let's just be maybe totally clear. We'll add in, the charge pump directly afterwards as well. And now really, if you sort of imagine, if I just take those charge pump outputs, and I just scale them by different weights for each one of those phase frequency detectors, and then all I do is I just add all those things together in the current domain. Right, and of course I feed this, through my loop filter, and then into the VCO, which then of course generates those 4 phases, right? Well, now by basically changing those coefficients, I can basically have the same effect as doing that phase interpolation, right? Because you can imagine if I put all of my feedback weight on this path, the loop will lock to 0 degrees, right? If I put all of my weight on this path, it'll lock to 90 degrees. If I put my weight somewhere in between those two, it'll lock somewhere in between, right? Now, the practical annoyance is that, indeed, if I really wanted to do this, I'd need like 4 dividers, and I'd have to make sure that, they all started up at the same time. So actually, the people who first did this didn't actually do this, with a divided loop. It was actually with a multiply by 1 loop, so they didn't have to worry about the divisions and things like that. But, at least in theory, you could do something similar even if you had the divisions in the loop as well. Okay? Yeah?
So can't you program the dividers rather than putting a coefficient, extra coefficient? Because
Program them how?
I mean, it's digital counter, right? So shouldn't that be easier to program? I mean, have
Well, when you say program, what do you mean?
I'm not sure whether it'll work, but I mean, having different count.
Well, okay, so I think what you're saying is, I believe what you're saying is similar to what Chintan was suggesting earlier, which was, imagine you just had a divider where you changed the feedback clock into that divider. So let's say on one phase you fed with the 0 degree, and then next time you fed it with 90 degree, and you dithered between them. Is that what you're sort of suggesting?
No, what I'm saying is you have 4 feedbacks, right, to the PFD. So have them at different counters. Can we do something?
Yeah, but so I think that's basically 4 separate dividers. And remember, most of the time your phase errors are not going to be larger than a clock cycle. In fact, they're probably going to be smaller than a 90 degrees, right? In fact, they should hopefully be much smaller than 90 degrees, because if they're bigger than that, you're probably making errors, right? So what's nice about this is that notice this node right here is low bandwidth, right? So all of the weird transient junk and errors that I might be sort of picking up here, kind of gets smoothed out by working on that low bandwidth node. As you'll see, maybe not today, maybe next time, turns out that this is probably actually a lot easier to build than a really good phase interpolator would be. Okay? Because again, here, I'm really just working on sort of average quantities. Whereas when I'm dealing with a phase interpolator, you'll see you have to sort of balance things just so nicely so that it really works the way you want it to. Okay? So by the way, I should also mention, this was done by some folks from Rambus. So it was first published in ISSC, but the journal paper is from John Poulton, and this was in JSSC December 2007. Okay? And this was for one of their first sort of, low power link kind of things. Okay? Again, turns out you can, there's lots of different potential ways you can do these things, but, some of these that we've just been talking about lately, or the last couple slides, they're again really nice when you have these heavily multiplexed kinds of systems where you really need to generate multiple clock phases all with the same sort of controllable phase offset. Okay? Make sense to people, or yeah?
Maybe this doesn't matter, but any mismatch on the paths on the feedback, or at least for the dividers, I guess the adaptation sort of takes care of it, or the CDR adaptation?
Well, no. So basically, if there really was mismatch on the feedback paths there, what that's going to translate into is essentially, potentially either, I shouldn't say errors, but it could change into, errors on the step sizes of your phase interpolation codes. Right? Now, if the errors on the feedback path are sort of constrained so that those errors are sufficiently small, meaning that your worst case steps are still within the range you want, then it's basically fine, right? So I wouldn't necessarily say it's more tolerant because, those errors would have caused the same effect even in these other kinds of architectures. But it does indeed mean that if there's some, let's say, transient glitch kind of thing that's associated with, the edges being too sharp or something like that, the fact that you're doing everything on the loop filter, that definitely makes things easier.
So I guess we came to this because we didn't want to have the mismatch of the multiple PIs.
Well, I wouldn't necessarily, that is an issue, although I wouldn't necessarily say it's the mismatch of the multiple PIs that's a driving factor. I think this is more just, it's a lot of hardware.
Sure.
Right? It's a lot of stuff to be building. Now, you could argue that, okay, well, if I have a bunch of PFDs, that's also a lot of stuff, but it's potentially at lower frequency and so on and so forth. Again, I wouldn't necessarily say that this is a slam dunk from the standpoint of saving you hardware. I think this is much more driven by doing all of the phase offset control in kind of a slow point, meaning at the charge pump, loop filter node, but still being able to do it with a full 360 degrees of phase shift. That's what I think the biggest advantage of this particular technique is. Okay, great.
So
yeah.
Question. So if you compare the two of them, then I guess a good trade-off is the first one. Because it's just...
yeah, this is a pretty reasonable thing to do. I mean, again, it depends on, you have to work out exactly what the context you're in and how much multiplication you need and, what the reference. But this is indeed, I think, a fairly reasonable approach as well. And indeed, people are using these kinds of things as well. Although, again, it's also heavily dependent upon how much multiplexing you're doing in the first place. Right? So if you're not doing very heavy multiplexing, for example, if you have a full rate system, then there's kind of no difference between doing this and just having the phase interpolator open loop to begin with.
What do you mean?
Because remember, the reason that you want to do this at all is just so that you get multiple phases all with that same phase shift on them.
Right.
But if I have a full rate system where I just need one phase interpolator anyways, it kind of doesn't really buy me anything.
Sure.
Yeah. Okay, great. So unless there's more questions on this. Oh, yeah.
So the taps are controlled. Can you do the tap control by changing the current for this?
What do you mean, tap control?
I mean the alpha, beta, gamma, and delta.
Oh, yeah, absolutely. I mean, in practice, what you really do is you just adjust the currents in the charge pump, or in fact, what you may even do is something like, either tweak the currents in the charge pump or have some switches and then just have like 2 really charge pumps with adjustable currents. Lots of ways you can really build this. Okay, so, in case you thought we were done, there's still actually a little bit more fun to be had in CDR. I guess nobody this time around did it, maybe because, I banged your guys' heads on how annoying it was to adapt these things. But nonetheless, actually, loop unrolled DFEs are still fairly common and popular out there, sort of in the real world, so to speak. So, it turns out if you do a loop unrolled DFE, then your life actually is fun not just because of adapting the actual value of the coefficients from the standpoint of doing the DFE cancellation itself, but actually it has some pretty direct implications on the clock and data recovery as well. Okay? So in order to see that, you can maybe kind of imagine that, remember with the loop unrolled DFE, there's basically multiple different sort of possible analog levels that could be going into your receive slicers, right? And that's kind of indicated by this diagram that I'm showing you here. Okay, but the easiest way to sort of see what the implications of that are in terms of your clock and data recovery is just to sort of draw, what's sometimes called sort of the trellis diagram. So what I mean by that is the following. So remember, in a loop unrolled DFE, at least if I just have a one-tap loop unrolled DFE, what I'm basically saying is that, okay, if my channel used to be, or if my channel that I've sort of dealing with is 1, and then a first postcursor of alpha, what I'm basically saying is that every data bit that I can get can have any one of 4 possible analog values, right? So it could have 1 plus alpha, 1 minus alpha, minus 1 plus alpha, minus 1 minus alpha. Okay? Well, since I'm interested in what this does to the CDR, then what I need to do now is think about, well, okay, what's going to happen when I have 2 sort of consecutive data bits? And in particular, what happens when those 2 bits are different from each other, when I actually have transitions, right? Because only when I have transitions do I really get sort of timing information, right? Okay, so the thing that sometimes is initially confusing to people here is that, remember, this alpha here, whether or not it's a plus or a minus, is correlated with what the value of the previous bit actually was. Okay? So you can't just draw lines from each of these possible points to each of the other possible points, because not all of those are real possible things to happen. Okay? So let's just start with actually the simplest thing. So let's say that I'm just transmitting a clock pattern, meaning I'm just sending 1, 0, 1, 0, 1, 0 at the full data rate. Okay? If I was doing that, what would be sort of the arcs that I should draw into here? Like, if this is the previous bit and this is the current bit, which analog levels can I start from in the previous bit? And which analog levels can I end at in the current bit? And by the way, I'll give you a hint for a clock pattern. The previous bit is always different than the current bit.
Where the signs are opposite?
Yeah, it's the ones where the signs are opposite, right? So as an example, I can go from 1 minus alpha to minus 1 plus alpha. Or I can go from minus 1 plus alpha to 1 minus alpha. Okay? So indeed, that's sort of my clock pattern. Now, I've drawn this as kind of a straight line. Remember, in reality, you might actually have some ISI on the edges. It may not really be a straight line, but let's just draw it as a straight line now for sort of the purpose of understanding. Okay? Okay, so this particular transition, or this particular type of transition, turns out to be a fairly simple one, because notice this center point here, which remember at the end of the day, you're looking for where do sort of the ups balance with the downs. That's conceptually always happening when those sort of edges cross over with each other. That center point there is centered around 0 threshold, right? Because notice the swing for both of them is symmetric around the 0 point. Okay? Okay, well, as we said, this was for a clock pattern. Well, turns out life is not always that easy. You don't always just get clock patterns, but you get other stuff too. Okay? So let's actually start seeing what happens with some of the other possible transitions. Okay, and so this is again sort of the same 4 data levels here. Okay? So now, what are some of the other transitions you can get? What are the other, let's say, possible things that you could get in terms of having arcs from one analog point to another? And by the way, I'll give you a hint. Just, start from some point and then see what would happen on the next data bit if you actually made a transition.
1 plus alpha to minus 1 plus alpha.
Yeah, exactly. You could go from 1 plus alpha to minus 1 plus alpha, right? And again, just to be clear, this would happen because I get the plus alpha here because the previous bit was a 1, right? Okay, so what's the symmetric arc that you would get? Like Like if I just flipped everything over, what's the symmetric arc?
-1 minus alpha to 1 minus alpha.
Yeah, exactly. This would be just -1 minus alpha to 1 minus alpha. Okay? Turns out there's actually a couple more transitions that we can get, but those maybe are not as interesting. We'll come back to them in 1 second. But I want you guys to notice one thing here. If I just draw a straight line down here in time, notice the zero crossing point of these transitions is most definitely not the same as the zero crossing point of these transitions. Okay, it's actually shifted over to the right. Okay, so this would mean that this, remember I showed you those, those distributions of what happened on the edge? Notice this would exactly create that bimodal kind of behavior we saw, or maybe even trimodal or whatever, right? Because you'd see that, for some kinds of edges, it was transitioning in one point, and for other kinds of edges, it was actually transitioning in a different point, okay? Now, it turns out there are indeed things you can do to sort of try and address this, okay? So in particular, let's say you wanted the ultimate highest performance system. So that means you're willing to throw as much hardware as you need to at this to make it so that you can get every single possible transition to give you good data about the timing. Any thoughts on what you could do to make it so that you would see equivalently zero crossings at the right time? By the way, what is the quote-unquote right time?
When your transition crosses the dotted line.
Yeah, exactly. So when the transition crosses the dotted line, that's really the right time for you to say, is the thing early or is the thing late, right? Okay, so what that basically says is that now, if I want to make this thing work, what I should basically do is, on this arc, meaning on the arc that goes from 1 plus alpha to -1 plus alpha, instead of deciding whether it's early or late, based on slicing at 0, instead what I should actually do is slice at wherever that voltage is that crosses that dotted line. Okay, so I'm just going to draw a dotted red line there, and another dotted red line here. Okay? Turns out if you just sort of look at it or think about the math a little bit, that dotted red line crosses at plus alpha. Okay, and the way you can see that is the sort of peak-to-peak swing here is 2. Right, so you go from 1 minus alpha to -1 plus alpha. Excuse me, the peak-to-peak swing here is 2 minus 2 alpha. Okay? Whereas here, the peak-to-peak swing is just 2. Okay? Because you go from 1 plus alpha to -1 plus alpha. So if you want to get sort of the same, let's say, relative center point, you have to shift up by alpha. Okay? Because basically, if it's 2 and you wanted to get it instead of being 2 to be at 2 minus 2 alpha, then the center point shifts by alpha. Okay? Similarly, you could take the other side and shift it down by minus alpha. Okay? Okay, so in order to really make this happen, notice we have to add some hardware, right? So now, before what we had, and I'll just draw this over here, before we knew that just to receive our data, right, what we already needed just because we were doing loop unrolled DFE was basically 2 samplers, right? And both of these, of course, were clocked by the data clock. So what you needed was something with a threshold of plus alpha, and another thing with a threshold of minus alpha, right? And this was just our standard loop unrolled DFE. Okay? Something that looks like that, right? Okay, but now what we're basically saying is that if we want to do clock recovery for this thing as well, then if we really want to, again, use every single one of those edges and make sure that it has the best possible timing information, then now notice we actually need 3 different thresholds. We need one at 0, we need one at plus alpha, and one at minus alpha. Okay? So in other words, we'd now have to draw 3 different comparators. So again, one with a plus alpha offset, one with 0 offset, and one with a minus alpha offset. And of course, all of these guys are clocked by the edge clock. Okay? Now, the thing that gets a little bit tricky here is to realize that maybe somewhat similar to before, but in a slightly different way. Remember that when you were doing these sort of up and down estimates, you would only really get an up or down information when there was a transition in the data, right? So in other words, you needed to know that the previous data was different than the current data. Now you actually need to know more information than that. Not only do you need to know that the current data was different than the previous data, but you actually need to know which kind of transition are you dealing with, right? Are you dealing with a transition associated with a clock pattern? Or are you actually dealing with a transition that's associated with one of these other types of data patterns? Okay? So just to make sure it's clear, as we said, this thing where you have the 0 threshold, that's basically something dealing with a clock pattern, right? So that means that you have something like 101 or 010, right? That would sort of be a clock pattern, right? Okay, for this upper guy over here, where I've shifted the threshold to be plus alpha, what kind of transition is that?
110.
Yeah, this would be a 110, right? Because if you look at the arc over here, the only way I can get to that top point is if both of the previous bit, the previous bit and the bit before it were both 1, right? And then I had a 0. Okay, so similarly, for that bottom guy there, what's the data pattern you're looking for?
001.
Yeah, 001. Okay? So what this is really kind of getting at is that once you start getting into this, what you're really doing is you're no longer just sort of blindly looking for whether there was a transition in the data at all, but actually you're looking for different types of data patterns, and based upon what those data patterns are, deciding what's the best way to actually make the decision based upon, or make the timing estimate based upon those patterns. Okay? Now, by the way, I should mention, this is kind of like building a fractionally spaced equalizer, right, in the sense that you're sort of canceling the ISI on the edge position, right? But it's just sort of, let's say, another way of looking at things in the sense that you're really only doing it for this one unrolled tap, right? And you're trying to do it in a way that you're sort of clever about when is it that you sort of use which estimate, okay? So it turns out that this general concept of doing this so-called transition filtering, which really just means looking for particular data patterns, is actually a pretty sort of useful concept to keep in mind. Because once you have this in mind, then you can actually use this not just necessarily to build, the highest performance system that you can think of, but in fact even to simplify systems that, may have actually been much more complicated if you didn't use this kind of idea. Okay, so just is there a question?
So I guess since the edges are not exactly linear, is there a good way to estimate what the threshold will be?
Okay, great question. So I don't think there's a great way, in the sense of I don't think there's any live way of doing it perfectly. There may be some sort of, let's say, hacks that I can come up with that in a non-live way would figure that out. But, to do it live, I think has similar problems as what the normal loop unrolled DFE has, in the sense that there's really no analog level that you're looking for that gives you exactly that information. I guess actually, to be fair, the only saving grace here is that you really could look for, sort of this point in time here, but that would assume that you locked in the right place in the first place. Right? So I'm not exactly sure as to how you would sort of check that, okay, are you really in the same time when you're doing the estimates this way versus that way? Actually, okay, maybe there are some ways you can do it, but,
Yeah, like initially you could look at the clock pattern, and then based on that, you could set the threshold, and then again, not start.
Yeah, so there may be some iterative
Right.
kinds of things you could do. I have to admit, I haven't thought about it too carefully. There's probably some way you can get it to work. It's just going to involve sort of a series of steps and estimating different things and stuff like that. You can probably do that reasonably well. You still, unfortunately, have the problem of this alpha for the data sampler you can never really directly get. But for the edges, maybe you have a little bit better of a shot. Question in the back? Or?
I was just about to ask, do you actually just set the alpha to be the same, or it depends?
Yeah, okay, so at least in the preliminary implementations that I know of, they did indeed try and set the alpha to be the same. Now, the problem is, of course, these are physically different samplers, so making it the same is, only true to within some certain approximation. But for the first implementations that I know of, indeed, people tried to actually make this the same. Okay? So just briefly on this sort of transition filtering, again, the key idea here is just, to try and only use edges that will have good timing information. or at least to filter the edges based upon sort of where you know the different characteristics will be. So again, in this context of, for example, the loop unrolled DFE, you might do something where, let's say you didn't want to build all of those samplers. But at the same time, you didn't want to suffer the penalty of just, trying to track the very different timing estimates that you might be getting. Okay, so this again may be your data path. But then what you could potentially do is on your edge path, instead of having all 3 of those samplers, you'd only have 1, right? But then what you do is you say, okay, but look, I'm only going to use this thing when I know that I actually had a clock pattern, right? When I know that I had a 101 or a 010, so that I know that that timing information is reasonable, okay? In fact, you can imagine you can keep on extending this to more and more taps. So you can try and make it so that you really only do your timing estimates based off of patterns that you know should have good information given whatever it is that you were doing in your equalizer. And by the way, you may even want to apply similar types of ideas even if you were physically closing the feedback loop. Right? If nothing else, just because when you were physically closing it, your DFE itself may not be settling exactly, at the right spot. Okay? Does this kind of make sense to people, or? Okay, great. So unless there's sort of more questions on this, I think we're basically out of time for today. We'll finish up with CDRs next time, and we'll talk some more about phase interpolators, and then you guys should be sort of totally set for finishing phase 3 of the project. So I'll see you guys on Thursday.